All right, this video is going to cover section 5.1, which is a part of our last unit. And if you're in my in-seat class, you are watching this because I am already out on leave. And if you're in my online class, then you're used to this already. So this is the same kind of deal as what you would get in a real in-seat lecture with me, but with um, just kind of voiceover lecture with the note sheet here um, so that you can see it. I am going to post these notes sheets into Blackboard so that you are able to print them out and fill them in as we go, the same way that we would if we were in seat. So you'll have access to all of these note sheets well, and then any additional sheets that kind of go along with some of this stuff. So it's looking like I'm going to end up covering this entire last unit with lecture videos. So here we go. I'm going to go over to OneNote and I'm going to insert that attachment of that note sheet that I just had. Let me save it first and make sure that I have the right one in there. Okay. And we'll go into OneNote and insert this is down in chapter 5. And so let's see. I'm going to be referring to another note sheet as well that's not going to be in OneNote, but I'll just kind of move it over whenever I want to talk about it so that you guys can see it pretty easily. I am going to be drawing some graphs in this section. And so if you have a graphing calculator, you might find it helpful to use. If not, that's okay. We are going to make a table and use a very few amount of values just when we are creating these different graphs. Now this first section is covering exponential functions and what their graphs look like. So we are going to be looking at some different curves here because that's what exponential graphs look like. And typically when we are graphing, we make a table of values. That is, again, unless you have a graphing calculator, in which case you can go ahead and just type in your functions so that you can see what they look like on your graph, and that's perfectly fine. If you're in my pre-calc class, I know you guys know how to use the graphing calculator. You are going to cover the same topics that we cover in college algebra for our last unit. So you guys will be seeing this as well, and you'll also have access to the same notes as well. So let's take a look at this first example. The first one here is y equals 4 to the x power. So what makes a function an exponential function is that it has a variable in the exponent position in your function. Now, when we graph these, we're going to make ourselves a t-table. And we're going to select values for x. Now, you want to select values for x that create a nice shaped curve so you can actually see what's going on. A lot of times we can use -1, 0, and 1, but sometimes those aren't the best values because they don't really give you enough information. If that's the case, it's fine. Just go ahead and pick a couple more values. I'm going to start with -1, 0, and 1 and see if we can get enough of a picture here to be able to draw our graph. So I'm going to start by substituting each one of these values into the function. And the first one is 4 to the -1 power. Now, you can evaluate these as fractions or decimals because you're going to be using them to draw the picture of the graph. So anything that's not an integer is just going to be a best guess placement anyway. And so we just want to make sure that we have a good idea of where these things are. And decimals are typically what we use when we're trying to draw pictures in a coordinate plane anyway. So if you plug in 4 and root it to the -1 power in the calculator, you get a decimal and it's 0.25. And so when we go to graph this, we'll just do our best to get it, near 1/4. When we plug in 0, we've got 4 to the 0 power. Anything to the 0 power is going to return a 1. The only thing that doesn't do that is 0 to the 0 power, which we're not going to be dealing with. But this one's a nice point, 0, 1. And then we've got 4 to the first power, which returns 4. So these 3 points are good enough to get me a nice looking picture. We've got a decimal, then we've got a couple integers, so it is going to give me a nice shape here. So I'm going to plot each one of these points. I start with -1 at 0.25, which I'm just going to have to kind of guess is maybe right around there. This is, a small little grid on here, and it's hard enough to write with this pen. So actually, it looks like I've covered almost the entire thing, but you get an idea. It's close to the x-axis. Second point is 0, +1, which is right here. And then third point is 1, 4, which is up here. Now, these curves that we're going to be making are going to look almost flat on one end and almost vertical on the other end. So this thing comes down and starts curving its way along the x-axis. And then on the other side, it almost goes straight up and down. And not quite, but almost. What this is doing is just growing very, very quickly. So it almost looks like it starts off flat and then shoots off up to the sky like a rocket. This first type of graph is an increasing graph, and it models exponential growth, where you start off small and then you get very high very quickly. Now, the second example has a base that is a fraction. So when we go to put this one in, we're going to have to use, if you don't have a fraction button on your calculator, you're going to have to use parentheses 1 divided by 3. So just kind of be careful when you're entering this thing in so that you can make sure that your calculator does the correct exponential power. So this time, when I put this into the calculator, I'm going to use parentheses 1 divided by 3 as my base, and I'll close it off, and then I will pick, or then I'll use the caret button to raise it to a power. I'm still going to start off by using -1, 0, and 1. And then if I have to add anything else in, I will. If I don't, then we don't have to worry about it. So hopefully this thing will work itself out well enough to make the curve without us having to add any extra things in. So the first thing I'm going to do is type in 1 divided by 3 and raise it to the -1 power. And if you raise 1/3 to the -1 power, you get a nice, neat little number, +3. That's because the -1 power is flipping this thing over and making it the reciprocal, 3 to the +1 power. So that's where this is coming from. Second thing we do is 1/3 to the 0 power. And just like before, when you raise a number to the 0 power, it returns +1. And then 1/3 raised to the first power is 1/3. Or if you put it in the calculator, it's going to give you 0.3 repeating, which is fine. Either way, it's not going to be a nice, neat little point like the other ones. So we'll just have to do our best. So now we're going to do the same thing we did before. We're going to plot these points and then create the curve. We start this time at -1, +3, which is right here. Second point again is at 0, 1. And then my third point is at +1, and then like 1/3, which is like right there-ish. And so this time the points start off higher on the left and are coming down lower. So that means that the almost vertical side is going to be on the left, and then it's going to come curving down on the right. So kind of backwards from the first one. We're vertical-ish on the left and flat-ish on the right. And this is an example of a decreasing graph, which models exponential decay. So there are a couple basic notes about these types of functions where you have a number being raised to the x power. and it's going to be based on whether you have an integer or a fraction or decimal as your base. So there's a couple things down here, and we've seen these. If the base is an integer greater than 1, it's going to give me an increasing graph. If it's a fraction between 0 and 1, then it's going to be a decreasing graph. So as long as it's bigger than 1, it's going to be increasing. It's these little fractions, a fourth, a third, a half. Whenever you raise those to a power, they're going to be decreasing. Now, in these basic functions, the domain is negative infinity to infinity, because you could plug anything in and get an answer. But the range is going to go from open bracket 0 to infinity. So it's always going to be shooting up towards the sky, and it's never going to quite reach the x-axis. Also, in these base functions, the y-intercept is going to be 0, 1, because anytime you plug in that 0, it's going to give you the power of 0, which gives you a 1. But there's not going to be an x-intercept, because in these ones, it doesn't reach the x-axis. Now, if we end up bringing in negative powers or adding or subtracting anything to it, that's changing the basic function, and that is going to give you something else, which is fine, and there will be differences in what the range does then, and there will be differences in the intercepts. You may have an x-intercept in that situation where you might be flipping the graph around. And so we are going to talk about some transformations like we do in section 2.5, but they're going to be transformations kind of going along with these exponential functions. So we'll talk about that in a second. Before we get to more involved exponentials, we need to talk about base E functions. So base E functions are functions that have an exponential base of the letter E, which seems weird, but the letter E is just an irrational number like pi is. Pi is 3.1415, it keeps going forever. E is also an irrational number that goes forever, and it's like 2.7182, and it keeps going. And this number is typically used in continuously compounding interest. It's used in some growth and decay formulas. So it's kind of like a constant number in these different formulas, and it's represented by the letter E. Now, there is a button on the calculator that allows you to evaluate E, because you're going to have to do some evaluations and some graphs where you use E as the base. So the button on the calculator that you use is second ln. If you look on your calculator behind the ln button, you should see as a function of your natural log button a little thing that says e to the x power. This second ln is what brings up e to the x power on your screen. And then you can enter in whatever the exponent is supposed to be. And when you hit equals, it's going to evaluate it for you. Now, most of the time, when you are evaluating E and raising it to a power, you are going to get an irrational number. So your solution will go forever. And therefore, we're going to have to round these things. And so we will round them to whatever the appropriate place value is. A lot of times it's 3 or 4 places. So it will just kind of depend on what Hawks asks for. And if we are graphing using base E, then we will use 2 or 3, whatever you can fit in your little table. So we're going to evaluate a couple first just so that we can see it. So e to the 4th power. We're going to hit second ln 4. Second ln is going to bring e up onto the screen. And when we hit 4 and hit equals, it's going to spit out our answer. Now, again, like I said, we're going to have to round this thing. Let's go to 4 decimal places. So this is 54.5982 if we round up, because it's 59815. We're going to do the same thing with this second one here. It is a negative exponent, so we are going to have to use the negative button as well. Remember, when you're using the negative button, it's not the minus key, it's the negative. Second ln, and then the button that has the minus on it typically has a parenthesis around the negative symbol, and then 2.458. We can put that whole thing into the calculator, second ln, negative 2.458, and when we hit enter, it's going to give me my solution, which again, I'm going to round to 4 decimal places. So this time it's 0.0856. And so evaluating E, and therefore graphing with E, is going to involve using the calculator for sure, because this is an irrational number that we're trying to raise to a power. The only time that it's not going to be necessary for you to use the calculator is if you have e to the 0 power, because even e to the 0 power is going to be 1. So let's graph a base e just so that you can see it. And again, we're going to kind of follow the same rules. We're going to make ourselves a table, and we're going to use the points -1, 0, and 1. And we're going to rely on the calculator to do this. So for each one, I'm just going to use that second ln and then put in my power. So for e to the -1, I hit second ln, -1 equals, and I get a decimal. The decimal I get is 0.3679, I guess if we round to 4 decimal places. 0.3679. E to the 0 power is 1. It's not an approximation, it is exactly 1. And then we do e to the first power, and that's just going to give us the number representation of e. It's still irrational, so we're going to round it, and I'm looking at 2.718. And now that's enough to see that we're starting off low in the decimals and gradually getting higher. So this thing is going to be an increase. And that makes sense because e is to be a little over 2. So that's a positive number that's higher than 1. And therefore, when we graph it, it should look like an increase, like it said in our little notes. So let's graph. -1.3. Or let's, I don't know, maybe that's right there. 0 is at 1. And then 1 is at 2.7-ish. 2 point, I don't know, maybe right here, 7. And so this one starts off low and is going to go up high. And there's our curve. The curve here doesn't look very different from the first curve that we looked at. The biggest difference is that we had to deal with more decimals than we did that time, because integers are usually easier to raise to powers. But again, because we have our calculator, it shouldn't be too terrible because we're going to be able to do all of these powers on the calculator. So there's your e function. And this is the basic function for an e graph. So that being said, we're going to talk briefly about transformations with these exponentials. And if your base is an e, it's this parent graph. And if your base is something else, then it's whatever that value is raised to the x power as your parent graph. Now, we talked about transformations back in section 2.5, which is in unit 4. So it wasn't that long ago. And it's what we do our QEP project over, so you had some practice with it back then. With exponential graphs, there are transformations associated with them as well. So here's where I'm going to bring up that other sheet just so you can kind of see it for a second. And the transformation information for exponentials is also included in all of these notes. So this is the transformation guide for this section. And it talks about all the same kinds of transformations that we discussed before. So vertical shifts, horizontal shift, reflections, and the stretches and shrinks. So in these examples, the base graph is 5 to the x power. That's just what was used in these examples. In your examples on Hawks or in these notes, the base function is probably going to be something different because it could be any value there as the base, especially getting into some E stuff. So we're just going to kind of keep that in mind. All right, so I'm going to put this over to the side and I'll refer back to it here a couple times, but it's probably best if you have one of these printed and in front of you while you're going through this so that you can actually look at it and find each one of these things. Okay, so translations with exponential functions. So these are going to have some extra pieces and not just a base raised to the x power. So this is where we're going to get into moving these types of curves around the coordinate plane. And we will also see reflections that go over the x-axis. So there is a situation that you could run into where you do have an x-intercept, and that's totally fine. There's also situations that you might have where your y-intercept is something other than 1. If this thing shifts up or down, the y-intercept could be at a different point, and that's okay too, because that's what's going to happen in these reflections, or these translations rather. So in these examples, you're probably going to want to have that sheet in front of you so that it's easy to identify which translations you're looking at. There are 2 translation examples here. So we're going to talk about what kinds of translations are occurring in the example, and then we are going to graph the translation function. Now, in section 2.5, we discussed graphing the base function and actually physically moving it. And that's fine if you want to go through each one of the translations individually. If you just want to sketch the graph of the function and you have a graphing calculator, just do it with that. But if not, just make a table and plug into the actual function itself rather than graphing the base and doing the movements. So you need to be able to identify what each one of these different things is doing to the function, but to draw the graph, I would probably just make a table. But we are going to talk about the translations. So first of all, I want to take a look at what we have here. And so we are dealing with y equals e to the negative x plus 1. When your exponential involves e, the base function is y equals e to the x power. If it was a number that had the exponent attached, then it would just be the number to the x power as your base. Now, this is all that should be here for our base function, which is the graph that we just created. Our new function has 2 things added into it in addition to what is in the base function. So the first thing that is added in here is a negative in front of the x. And the second thing that is added in is a plus 1 after the x. Notice that both of the added pieces are found in the exponent because that's going to make a difference. Pieces that are found in the exponent mean one thing and pieces that are outside the exponent mean something else. So I'm again going to refer back to my sheet. I'm going to bring this over here so we can look at it. And now I had a negative in the exponent and a plus 1 in the exponent. So we are looking here for a negative being in the exponent and something added or subtracted to the exponent. So if we look here at this sheet, the negative being found in the exponent is right here. Y equals 5 raised to the negative x power. So when that happens, the negative in front of the x creates a horizontal reflection. That means it's reflecting the graph over the y-axis. So if you remember what happens there, when you reflect the graph over the y-axis, all of the x coordinates in your points change signs. So it's going to kind of flop it just from one side over to the other side. Then we're looking for something being brought in and added or subtracted into the exponent, which is right here. And that would indicate a horizontal shift. Now, in this one, they used x minus 1. That's fine. We have x plus 1. Regardless, you're going to change the sign to move it. So we have a plus 1 in our graph. We change the sign to minus 1, which means we are going to be moving it to the left. When you move a graph to the left, you subtract that value from each one of the x coordinates. So you could go through and do all of these transformations like this, or you can say what they are and then make a table. So I'm going to say what each one of these transformations are so that we know exactly what it is, because it's going to ask, do you reflect, where do you reflect it, and so on. So we said the negative in front of the exponent is a horizontal reflection. That's going to flip it over the y-axis. And the plus 1, remember plus 1 means it moves it to the left. This is a horizontal shift. And it's left 1 unit. Those are the only two things that are happening to this base function. So any other things that it's asking you about, you don't have anything else. This is it. So x coordinate, negative 1, 0, 1. Let's see if we have enough here to make ourselves a nice picture so that we can actually plot this thing and get a good idea of what the curve looks like. If not, just add another point or two in there and it's not a huge deal. So we want to graph e to the negative x power. Oh my gosh, my calculator stopped working. There we go. E to the negative x power plus 1. And now I'm going to use these 3 points to begin with, negative 1, 0, and 1. So I go into my function with, starting with negative 1, y. And so when I plug in, I'm looking at e to the minus negative 1 plus 1 power. And that's just me plugging straight in here. I'm going to simplify it after I get everything in, but I want to make sure I have everything in there correctly. So e to the minus negative 1 actually means e to the first power, because minus and negative means plus, and then plus 1 more, which gives me e squared. So e squared is going to give me, if I go into my calculator, I get 7, I can't hardly fit this either, I get 7.3, I'm just going to do 2 decimals because that's all I can fit. So 7.39, which is a good enough idea of where we're at. So a little bit higher than what we've been doing, but that's okay. And now we do the same thing with 0. So we've got e to the negative 0 just means 0 plus 1. So this is e to the first power. And e to the first power is that 2.718. So I'll just do 2.72. And then I plug in 1, and I've got e to the minus 1 plus 1. And negative 1 plus 1 is 0, so e to the 0 is 1. So we can see from our points that we are starting off on the left-hand side high up at 7.3. So I'm negative 1, 1, 2, 3, 4, 5, 6, 7.3-ish right there. Good enough. 0 is at 2.7, maybe right there. And then 1 is at 1. So this time our graph is starting off high and coming down low, and it's going to flatten out almost on this end, like so. Well, not like that, but you get it. Let's see if I can fix that. Try harder. This pen is something. There we go. And if you think about it, based on what kinds of shifts were supposed to happen, it makes sense that it would be facing the other direction. It was supposed to reflect over the y-axis, which would flip it around on that vertical axis. So it would make the flat side go the other way and the vertical side go on the opposite side. And then it shifted left 1 unit as well, which is kind of changing how things look on our coordinate plane. Now this also changes the y-intercept. You can see that the y-intercept has moved up. It was 0, 1. Now it's 0, 2.72, which is fine. That again is just based on the fact that we had some motion in our graph. So we can state what the different transformations look like, and then we can just go ahead and do the same thing we did before and make a table and kind of handle all of the graphing at one time. So let's look at another example, this one having numbers in it. And so numbers are similar to E, except usually a little bit nicer because you get nicer answers whenever you put this stuff in the calculator, which is good because then you're not dealing with a bunch of decimals usually. So if we are dealing with this one, this time the piece that has the variable exponent is the 3. So we're going to say our base function here is y equals 3 to the x power. Now we need to determine what kinds of things have been added in here. And this time 3 different pieces have been added. We have a 4 added in. It's a positive 4, not in the exponent, but down at the bottom. We have a negative in front of the 3, and we have a negative in the exponent. Now, we just talked about what a negative in the exponent does, because the same thing happened in our e function. So when the negative is in the exponent, again, that should indicate to you that you have a horizontal reflection, which means it flips it over the y-axis, and it's going to make this normal curve go backwards from what it normally does. Then we have these 2 other pieces that we haven't seen. So I'm going to, again, bring my little sheet over here so we can look at it. This time we have a number added in to the actual main function here. And when you have a number added into the main part of the function, not in the exponent, but just down here in the bottom, we use the same sign to move the graph up or down. So if we have a positive number, which we do, this is going to be a vertical shift up, in our case, 4 units. Then we also have a negative in front of the entire thing. Not the entire thing. I said that kind of, I don't like how I said that. It's not in front of the entire thing. It's in front of the base function. So our base graph was 3 to the x power. We have a negative in front of our 3, which means that in addition to the fact that we had a horizontal reflection, we are also going to have a vertical reflection. Vertical reflections reflect over the x-axis, which means not only is this thing going to be backwards, it's going to be flipped upside down as well. So this is a vertical reflection, and that's over the x-axis, causing this thing to flip upside down. So we're upside down and backwards. And then also this positive 4 is a vertical shift up 4 units. Now you could do each one of these separate, where you do your reflections and then do your vertical shift, but that takes a little while. And you also have to base everything off of your base graph table. So rather than go through each one of the individual, excuse me, the individual reflections and shifts, I'm going to go ahead and just make a table and do all of it at one time. So I am going to use -1, 0, and 1, and then we'll see if that's enough to kind of give us a good idea. Maybe we'll add something else in here just to get a better idea. -1, 0, 1. All right, so -1, making sure I have enough room this time, 0 and 1. Alrighty. So I'm going to start with -1. So I've got 4 minus 3 to the -1 power. Because it's minus, then negative. So again, we're looking at 4 minus 3 to the first power, which is 4 minus 3, which is 1. Well, that's nice. That one's not terrible at all. -1, 1. Plugging in 0, we've got 4 minus 3 to the, remember, -0 doesn't mean anything, so it's just 0. And 3 to the 0 power is 1, so 4 minus 1 is 3. Then we've got 4 minus 3 to the -1 power. And this time we are going to get a decimal because 4 minus 3 to the -1 power is 0.3 repeating. So this time we get 3.6 repeating. And so we're at 1, 3, 3.6. Let's add in another one just for fun. And we can go to either end that we want to. I'm just going to do a 2. Just to add something in on this side. If you want to go with a -2 just to get something else, that's fine. And you don't even have to do this if you don't want to. I just want to have a better idea. So this is 4 minus 3 to the -2 power. And this time, 3 to the -2 power is going to give me an even smaller number, 0.1 repeating. So 4 minus 0.1 repeating is 3.8 repeating. And now we have a kind of an idea of how this thing is going to look because it's starting to flatten out here. We're not getting much bigger as we go. And you're going to see that that's exactly what this thing would have done. So let's plot these points and see what they look like. We've got -1 is at 1. We've got 0 is at 3. We've got 1 at 3.6. And we've got 2 at 3.8, which is barely higher. So you can see that this time it's flattening out over here. And on the opposite side of the flatten, it's supposed to be straight almost. And so this one has kind of flopped itself all around. Normally these graphs are curving in this manner. This one is upside down and flipped around so that we have our two reflections. And then it's also moved up quite a bit because we have this +4. And if you want to see each one, you can do each one individually to see this thing move. And then you can kind of see how it moves. And that's how we did this whenever we did the 2-5 translations. Each individual move was kind of shown so that you could see each one. I'm trying to save time here so that I can make sure that everything gets covered and you guys aren't bogged down with a ton of stuff. So that's the graphing. And again, if you have to identify translations, you can refer to that sheet. And a lot of times you're going to be selecting the graph out of a picture, but there are going to be times whenever you're drawing the curve. All right, so that's graphing. We've seen regular exponentials, we've seen e exponentials, base function graphs, and translation graphs. Now we're going to get into some exponential equation solving. And in solving, excuse me, these exponential equations, this is going to kind of lead us into what other types of things are in this unit, because there is going to be quite a bit of equation solving when we get to section 5.5. So this is kind of like a little intro. Now there are a couple different ways that you can solve exponential equations. This is the first type of exponential equation, and in this exponential type of equations, you are going to be able to rewrite the bases so that they can match each other. The reason why we would want to do this is because there's a property that says if you have the same base raised to some different powers, then you're allowed to drop the base and just set the exponents equal to each other. If the bases are the same, then the powers have to be the same. That's the only way that that can be true. So what we want to do is try to rewrite one or both of the bases so that they match each other. And we are going to be taking larger bases and making them smaller numbers raised to a power. Put a little note there. So for example, if you had, I don't know, 25, you could rewrite it as 5 squared. If you had something like 81, you could rewrite it as 3 to the 4th power. So we want to take these larger bases and make them a smaller number raised to an exponential. That should help us rewrite these with the same. Now, there are going to be times where you have to rewrite both of the bases as a smaller number. It will just kind of depend, but I always start with the bigger one and see what I can do. So there's a couple examples here. We're going to start by rewriting the equation so that our bases match. So in the first one here, we've got a base of 4 and a base of 16. So the first thing that I ask myself is, can I rewrite 16 as 4 to a power? If I can, I want to do that. And in this case, you can, because 16 is the same thing as 4 squared. So if I rewrite 16 as 4 squared, which I'm allowed to do, this base matches the one that's on the other side. And now we have an exponential equation that kind of sets up this property here. Same base, and when we have that, we're allowed to throw the base away altogether. Then we set the exponents equal to each other. So if negative x equals 2, to get x by itself, we're going to divide both sides by negative 1. And there it is. Now, in this second example here, we have a 9 and a 27. We ask ourselves the same question to begin with. Can I rewrite 27 as 9 to a power? Now, before you get all excited and start thinking 9 times 3, that's not how this works. You have to be rewriting it using exponentials. So, 27 is not a power of 9. 9 to the first power is 9, and 9 to the second power is 81. It skips right over 27. So we have to do something else. So the next question I ask myself is, okay, if I can't rewrite 27 as 9 to a power, are they both a power of something else? And the answer to that question is yes. 9 is 3 squared, and then we have its power, 2x minus 5. And 27 is 3 cubed, again, already being raised to the x minus 2 power. Now, the bases are the same, But before I drop them, I'm going to simplify these exponents because it doesn't look right like that. So we have to think about our power rule. The power rule says that when you have a power being raised to a power, you multiply the powers together. So this is 3 to the 4x minus 10. This side is 3 to the 3x minus 6. Now it just looks a little bit nicer. So we can go ahead and drop our bases. And now we have some expressions, and that's all right. 4x minus 10 equals 3x minus 6. This is a pretty basic linear equation. And I'm going to go through my steps for solving. First thing, let's move this 3x over. When I subtract 3x over to the left, I get 1x minus 10 equals negative 6. And now this is a one-step equation because there's only one thing to move. To get x all by itself, we're going to add 10. And we get x equals 4. And there's your solution. So sometimes you can rewrite one as the other. Sometimes they both have to be rewritten as something else. And it will just kind of depend. All right. 3 and 4 are at least still living in the number world, so that's good. We've got 7 and 1 over 49. First of all, 1 over 49 is not in a good form. It's in a fraction form. And I can fix that really easily if I just use a negative exponent. So instead of 1 over 49, I'm going to rewrite this as 49 to the negative 1 power. Now, normally we don't like to do that, but in the case where we're trying to eliminate these bases altogether, I'd rather have this thing as an integer to a negative power than as a fraction. And I'm allowed to do that if I want, and it's helpful in this case, so I'm going to do it. So I'm going to start there. And then I should say to myself, 49 is 7 squared. So I'm going to rewrite 49 as 7 squared to the negative 1 power. Again, I'm allowed to do that. And just like in the last one, I have a power being raised to a power. So the power rule says, let's not do that. Instead, let's multiply these powers together. So 7 to the x squared plus 3x power equals 7 to the negative 2 power. Now the bases match, so let's drop them out. We get x squared plus 3x equals negative 2. Now this one's a little bit different because it ends up with a quadratic equation. And when you have a quadratic equation, hang on. When you have a quadratic equation, you typically are going to end up getting two solutions. So we might want to check our answers this time just to make sure they both make sense because sometimes it's not going to. So we'll check this time. But I'm going to start by adding my 2 over. That's going to give me x squared plus 3x plus 2 equals 0. Now this has to be solved using a quadratic method. And we can use whichever one we want, but I would probably factor because it's fastest. So I'm looking at x plus 2, x plus 1 for my factors. And then for my solution, set each one equal to 0. So if x plus 2 equals 0, then x would be negative 2. And if x plus 1 equals 0, x would be negative 1. Now I want to come off and check. I don't have like any room here. Let me see if I can move this a little tiny bit. It's kind of come off to the side a little bit. I'm going to have to come like over here. I don't like to do that, but I need to be able to check these just in case. So we're going to check 3. All right, so we're going to start with negative 2. So this is 7 to the negative 2 squared, plus 3 times negative 2, and it's supposed to equal 1 over 49, so let's see what happens. Negative 2 squared is 4. I wish it would not do that. And 3 times negative 2 is minus 6 equals 1 over 49. 49. Stop doing that. 4, 9. 4 minus 6 is negative 2. 7 to the negative 2 power is 1 over 49. So that one works. Negative 2 is good. Let's see if negative 1 works. So we've got 7 to the negative 1 squared plus 3 times negative 1. Negative 1 squared is 1. 3 times negative 1 is negative 3 equals 1 over 49. And yeah, that's negative 2 also. So 7 to the negative 2 equals 1 over 49. Yes. All right, so these two answers both work. Good. That is good news. Both are good. So if you have two answers that work, fantastic. Just make sure that when you put them in, you use a comma to separate. Do not put parentheses around them, or it counts it kind of like an ordered pair. So we don't want to do that. So good deal. Let's look at, I don't want that color. Let's look at number 4. So number 4 is dealing with 8s and 4s. No fraction bases, so that's good. We don't have to rewrite. But we cannot write 8 as a power of 4. So we're not going to be able to use 4 as our base. Instead, we will rewrite both of them as 2 to a power. So 4 is going to be 2 squared to the 2x minus 5. I wish this pen would write a little tiny bit clearer. I guess it's operator error though. On the other side, it's 2 to the 3rd power, and this time it's being raised to the x over 2. So that kind of stinks, but it'll be okay. We're still going to simplify by multiplying these powers. So on the left, we have to distribute. This is 2 to the 4x minus 10. On the other side, it's 2 to the 3x over 2. Oh well. Let's drop our bases, since we're allowed to do that now. We're in simplest form here. Throw these bases out, and we get 4x minus 10 equals 3x over 2. Now, this is still a linear equation, but it has a fraction involved in it. So you have more than one option, and it's really your call. You're welcome to leave this fraction in here and work with the 3/2 x, or you can do the little trick that we did back a million years ago when we got rid of fractions in our equations. So I'm going to get rid of it by multiplying everything in the equation by 2 just to get rid of it. That gives me 8x minus 20. And on the other side, the 2's cancel, so I've just got 3x. And now at least it looks a little bit better. And again, you don't even have to do that if you don't want to. If you want to leave the 3/2 x in there, go for it. Totally fine. Now from here, I'm going to solve my equation. I would probably subtract the 8x over, but most people don't go that way. So I'm going to subtract the 3x over just because I feel like that's how most people are going to go from here. So I minus 3x over. When I do that, I get 5x minus 20 equals 0. So now, don't forget that if you move everything away from one side, there's a 0 there as like a placeholder. So it doesn't just disappear. And now I have to solve this equation. So two-stepper, oh, wrong one. 2 steps, I need to add the 20 over. That gives me 5x equals 20. And then divide both sides by 5, which gives me x equals 4. So not too bad on that one. Even though it had a fraction in it, we still got a nice answer. If you get a fraction answer, it's fine, but nice answers are nicer, so most people like integers. Now this guy down here, I'm going to need some room for, so I'm going to move this thing up. And this thing here, I'm going to simplify this stuff that's on the right-hand side here. E to the x times 1 over e to the 3x. I don't like how that's written, and I'm going to make my life easier by rewriting it in a different way. So instead of going to leave these separate, I'm going to write it as 1. So e to the x over e to the 3x. It makes it a little bit more obvious in this form that this can be simplified. The rules say that if you have a quotient where the bases match, you can subtract their exponents. And if I do that, it's going to make my life a lot easier because this will be a single expression. So e to the x plus 2, and then it's cubed, equals, on this side, it's e to the 1x minus 3x, which is negative 2x. And that's okay, because again, it's better to have it written like this in a single line than to have a fraction involved. So I'm going to leave it with the negative 2 power, even though we normally don't do that. Now also, you notice that both of these sides have a single base e, which means we're going to be able to throw that base out. I am going to simplify this power, making it e to the 3x plus 6 power, and on the other side, e to the negative 2x. Again, that's just going to make it a little bit more obvious. You can throw these bases out because they match. So e's cancel. We're left with 3x plus 6 on one side, negative 2x on the other side. Now this equation looks just like the other equations that we've been doing. So we're going to solve this thing. And again, I would probably subtract the 3x to the right. A lot of people are going to add this 2x over to the left. It's fine as long as you remember to put in the 0 like we did in the last example. But I'm going to go ahead and subtract the 3x. We get 6 equals negative 5x. And then to get x by itself, we divide by negative 5. So this is negative 6/5. And there you have it for your equations. Now you will also see situations where you cannot rewrite these bases so that they match. And in that case, you can't do this little trick that we've been doing because the bases don't match each other. And the only way you can apply that little rule is if they do match each other. So in the situation where your bases can't match, we have to use another method. So that's going to come in section 5.5, and it's going to be based on how logarithms and exponentials are related to each other. So we are going to see that later on. But for now, for this section, the bases are going to match each other and look really nice and let you apply that rule. So that's all for section 5.1. Section 5.2 is going to get into some applications. So we're going to be dealing with how these things are actually used in the real world. And then after that, we'll start talking about the logarithm stuff. So I hope that this is just as helpful as whenever you had me in class. The only difference is that you can't see me waddling back and forth in front of the board. So hopefully this is helpful. If you have any questions at any time, remember that you can feel free to contact the department head, Ms. Pearson, or you can see Ms. Allen here on Liberty Campus for tutoring. If you're in the online class and you are closer to the Savannah campus, there are tutoring times available at that campus as well, and all of the tutoring times are listed as the last page of the syllabus. So if you need any help, just make sure that you reach out and contact someone, and hopefully everything's going well.